we were speaking about vibrational spectroscopy, IR spectroscopy. The introduction is given. So let us recall infrared spectroscopy is widely used in both research and industry as a simple and reliable technique for measurement, quality control and dynamic measurements. Some part we have already discussed. And let us see how the output of an infrared spectroscope will be looking like. The band position in IR spectrum are presented here as a frequency. Of course, we know that the frequency is inversely proportional to the wavelength and the directly proportional to wave number as well as the energy. So it's represented as the frequency in general as the wave number in one axis, along one axis. And the band intensities can be expressed as the transmittance or the absorbance. These are complementary to each other. Let's see the other. The T is the ratio of the radiant power transmitted by the sample to the radiant power incident on the sample. So it's the radiant power transmitted by the sample divided by the radiant power incident on the sample. And the absorbance is the logarithm to the base 10 of the reciprocal of transmittance. So you can have an equation that is A is equal to log 1 by T. So let's see in the graph. So in the instrumentation, IR spectra are acquired on a special instrument called IR spectrometer. Little details are required about IR spectrometer. We'll discuss it later. So the spectrum will be looking like this. See here, if you look at this spectra, here percentage of transmission along one axis, and here it is absorbent along the same axis. Here wave number, it is same everywhere, wave number. And here if you see the transmittance is directing downward, whereas absorbance directing upward. Here actually what is the sample accepted or absorbed, that will not be highlighted. What is the highlighted is this is emission spectrum and this is absorption spectrum. The second one is absorption. That's how you can understand. So these are the two ways of representing the IR spectra. One is the percentage of transmission versus wave numbers, and the other one is absorbance versus the wave number. Both will be done by the IR spectrometer computer. You can take any spectrum, whichever you like. And the infrared spectrometer, there is something which is connected to what we have learned in IR spectrometry. So you will be getting like this in the spectroscope, the instrument, but the spectrum will be look like this. So this process from here to here is done by Fourier transformation. The signal is recorded as a function of the optical path, the difference between the fixed and the movable mirror. It's a term related to the instrumentation. The interferogram contains the basic information on the frequencies and the intensities. The interferogram means this one. This is what we get at the initial point from the spectroscope. Frequencies and intensities, characteristics of the spectrum, but in a form of that is not directly interpretable. If you look at the spectra, I won't understand anything. So you need to make it or convert into the form of understanding. So that's what we do by Fourier transformation. The information is converted into more familiar form and the spectrum using a form that is the spectrum using Fourier transformation methods. So with an infrared data station, the computer acquires, processes and stores, retrieves spectral data. So if somebody asks you what happens during the Fourier transformation in IR spectroscopy, you can use this slide to answer to the question. Now, let's see what are the important parameters in the IR spectrum. One is the strength of the peak, and the second one is the position of the peak, and the third one is shape of the peak. We'll cover one by one. So if you look at this example, this is the spectrum of trans 2 pentene. Trans 2 pentene. This is the spectrum of trans 2 pentene. And here in trans 2 pentene, you have two options, that is cis isomer, the other one is trans isomer. Can you differentiate the cis isomer from trans isomer by using an infrared spectroscopy? Yes, you can differentiate by using infrared spectroscopy. The idea is cis trans isomer is symmetrically substituted and it does not absorb at all. When symmetrically substituted, it does not absorb, understand. And cis isomer absorbs more strongly than the trans isomer. Cis is less symmetrical than trans. The strength of the C double bond C stretch can serve to differentiate between cis and trans isomers in the above spectra. What is that hidden point? You have to think and tell me. So we already discussed what makes a compound to be IR active. So here the cis is less symmetrical. So what will happen? When it is less symmetrical, it will have more polarity. Am I right? Just recall. Then this is trans 2 pentene. And if you take cis 2 pentene, this is cis 2 pentene, the difference is the very weak trans C double bond C stretch. Here it is visible, very visible. CC stretch is notable. So, what is the question from this, if you ask? So, this point is very important. How do you differentiate cis and trans? Trans will have very weak stretch, whereas cis will have a strong stretch of the double bond, which is concerned about the cis and trans geometrical isomerism. So the question, so you hope you understood, cis will have a strong band and trans will not have a band at all, maybe a weak band. So the question is, why absorptions stronger or weaker are stronger or weaker? So let's take acetone. You imagine the structure of acetone. It has 6 CH bonds. 6 CH bonds, both the CH3. Stretching frequency comes somewhere 3000 to 2900 per centimeter. So please note this, it is supposed to be inverse. And 1 CO bond. That is what the acid of an acetone. CH3, CO, CH3. There are 6 CH bond and 1 CO bond. CO bond stretching frequency comes somewhere around 1715 per centimeter. In IR spectrum, the absorption corresponding to CH stretches are less intense than those for the CO stretch, even though there are more CH bonds than CO bonds. So, in the acetone, there are 6 CH bonds and whereas only 1 CO bond. If you look at the spectrum, you could see a strong peak for CO bond and you can see very weak stretching band for 6 CH bond. Why? So you can look at the diagram. This is what for CH and this is what for CO. Why? The answer to the question, one difference worthy of exploration is the relative polarity of the two bonds. CO bond is more polar because it is between carbon atom and oxygen atom, have a good difference in electronegativity. The other one is CH bond, where the difference is lesser. In the IR spectrum, the less polar CH bond has smaller absorption intensity than the more polar CO bond. So we can conclude like this. In general, less polar cause weaker absorption, that is smaller peak than more polar bonds. The CH bonds in 4-octane, another example is, are slightly polar, whereas C triple bond C bond is non-polar because it is symmetrical. In the IR spectrum, the CH stretches appear 29632 to 2669 inverse centimeter, whereas C triple bond C stretches, which is usually occurs at 2200 per centimeter, so weak that it cannot be seen. കാണാൻ പറ്റാത്തത്രയും ചെറുതായൊരു പീക്ക് മാത്രമാണ് സി ട്രിപ്പിൾ ബോണ്ട് സിക്ക് നമുക്ക് സ്പെക്ട്രയിൽ കിട്ടുക. വേണമെങ്കിൽ ഉറപ്പിച്ചോളൂ. So it comes here. It's very small. Whereas if you take CH, it is more polar than this, so you get a strong peak. The same bond polarity effect causes CO stretch absorption to be more intense than most other peaks in the IR spectrum. If you take IR spectrum of any compounds, wherever you have the possibility to see the presence of a CO stretching frequency, that stretching frequency will be always stronger. So carbonyl compound will have a strong peak in the IR spectrum. That is the moral of the story. So carbonyl stretches occurs 1850 to 1650 per centimeter, a region of the IR spectrum that usually does not contain any other intense peak. We'll come back to this point later. Now, the IR peak is characterized by its stretching frequency in per centimeter or centimeter inverse, its intensity, strong or weak, and shape of the peak, broad or narrow. And the stretching frequency we have already discussed. Now, what is that shape depends on? Shape means sometime it will be very narrow like this, sometime it will be very broad like this. And the question is, what is the shape depend on? You have to think about it. Okay, keep the question in your mind. And I'm talking about a very, very important point. Now we will focus on 4000 to 1450 per centimeter portion, centimeter inverse portion, that is the region like 4000 to 1450 of the IR spectrum. And this region is called the functional group region. The segment of IR spectrum below 1450 per centimeter is called the fingerprint region. It's quite complex actually. The fingerprint region contains many absorptions, and the complex pattern of the peaks in this region are unique for each compound, just like our fingerprint. So they can be used to confirm that an unknown is in fact the suspect compound. So you can't look at a single peak in this particular region, that is below 1450 region. You need to take a few peaks together, and that will give an idea about the compound. So 1450 below that, it is quite complex. Whereas 4000 to 1450 portion will give very definite and finite, clear peak for the functional group. So fingerprint region is an important term. So let us take few examples. Examine the IR spectrum. What are the significant absorptions in the range of 4000 to 1500 per centimeter? I am giving a spectra, you have to see actually. So look at this spectrum. So you could see the value 5000. See, this is 500, 1000, 1500, 2000, 3000, 4000. Let's see. The spectrum has a complex set of peaks 3000 to 2800 per centimeter, which correspond to Sp3 Ch bond stretches. So this is what 2000 to 2800 to 3000. It's a bit complex. See here, if you see, you can see, and all these peaks correspond to Sp3 Ch bond stretches. I hope you have learned the theoretical background of the IR spectrum. So what are the possible vibrations that could happen for this Sp3 Ch bond, and the possible vibration will lead to the particular peak in the IR spectrum. So we'll take all together for the Sp3 Ch. That's what represented to 2800 to 3000. The intensity of the Sp3 Ch stretching absorption varies widely depending upon how many Sp3 Ch bonds are present. So the intensity means this one. Okay, it depends on how many Ch bonds are present. The hexane spectrum also has a prominent peak around 1450 per centimeter due to Ch bending vibrations. So 1450, it comes somewhere over here. This one, it is due to Ch bending vibrations. So like 1450 or 3000 to 2800, what are the peaks available? It is the natural it is the nature of the compound. It absorbs over here. You must have learned the theoretical background. So if you are getting, suppose if you are analyzing an unknown compound and you are getting peaks like this, then you can understand it as the discussing compound. That's how it is supposed to be. The Cc single bonds are also common features of organic compounds. Their stretching vibrations occur 200 to 800 per centimeter and are generally weak. So this slide talk about Sp3 Ch bond stretches. So if there is an Sp3 Ch bond, what are the stretches? What are the wave numbers which is concerned about this particular compound you are going to observe? That's what we are discussing. So one is this, another one is this, another one is this. Then in the spectrum of one decene, this is triple bonded compound, what significant peaks 4000, 1500 are characteristics of our alkene? So before we were discussing about, this is actually a saturated compound because Sp3 Ch. This is unsaturated. Unsaturated means alkyne. So let's see what are the peaks. A strong absorption around 3300 and a moderate absorption around 2200. So 3300, a strong absorption, 2200, another a moderate absorption. This is not weak actually, a half, sized peak is there. And 3000 per centimeter, this one 3300 is due to Sp-Ch stretch. So C double bond C, this Sp stretch. The hydrogen at the end of the chain, and the 2200 per centimeter absorption is due to Cc stretch. So this is Cc stretch, this one, and the 3300 is due to this hydrogen. So one side, if you take this one decene, one side there will be a Ch bond. That Ch bond is leading to this absorption stretch. Examining the IR spectra of many terminal alkynes reveals that the typical Sp-Ch stretch peak usually strong and occurs 3320 to 3280. So you got a range. Here you got 3300 and this is generalized. You got a range. So if there is an Sp-Ch bond, you can see a peak somewhere in between of this. The absorption due to C triple bond C stretches are of variable but usually moderate in intensity and in 2260 to 2100. Idin edayile 2260, if it comes in between 2100, there is one possibility that is due to CC triple bond. So here the take home, you got two values. One is 3300, it is due to Sp Ch bond stretching frequency, and 2200, it is due to C triple bond C stretching frequency. Then examine the IR spectrum of 1-pentene. We have discussed about alkane, we have discussed about alkyne, now we are discussing about alkene. So this is an alkene, a typical alkene. The compound is 1-pentene. So what are the characteristics of this spectrum? If you see, alkenes can have from 1 to 4 substituents. So when it is an alkene, it can have 4 substituents because both the terminal carbon atom will have 2 valences. So the spectral possibilities are more complex than for alkyne. Alkynes, you have only CH bond at the terminal position. So that CH bond will appear with a stretching frequency, we already know. So too strong absorption around 3080 and 1645 per centimeter, as well as a weak absorption at 1782 per centimeter. So you got input. If you are taking alkene, this is 3080 is one possibility, 1645 is another possibility, 1782 is another possibility. What are the reason for that? 3080 per centimeter P correspond to stretching of vinylic CH. 1-pentene, vinylic means like C double bond C, this hydrogen. Not it is approximately to the similar Sp3 Ch bond. So this value, it comes, we have already discussed the Sp3 Ch, it comes almost similar to that. In general, vinylic CH stretch peaks for alkenes appear 3100 to 3000 inverse centimeter and are usually strong. So this point should be understood. You have to note this point that 3100 and 3000, if it comes in between this with a strong peak, then there is a possibility of vinylic hydrogen. The 1645 inverse centimeter peaks are caused by C double bond C. So we got another data, 1645 is due to CC double bond, and the CC double bond may appear somewhere in between 1680 to 1610 per centimeter and is of variable intensity. And we can't assure what could be the intensity. It can be weak or strong or moderate. The IR spectra of terminal alkenes, but not other alkenes, sometimes also include a weak absorption, that is 1780 centimeter inverse. See, look at this spectrum. This is very important. You have to observe it. We were discussing about cis and trans. Cis-trans isomerism, symmetrically substituted, does not absorb at all because it does not have any polarity change. So cis isomer absorbs more strongly than trans isomer because cis is having a polarity, it is having a dipole moment, so it absorbs. Cis is less symmetrical than trans. The strength of the CC double bond stretch can serve to differentiate between cis and trans isomer in the following data. See here, we have already discussed this. Okay, this is the blank one to compare. The CC stretching frequency is lower if the alkene is strained or conjugated. This is another point. The CC stretching frequency is lower, means like lower comes this side. If there is strained, angle strain or some strain like that, or if it is conjugated. Like alkenes, we have, if you are multiplying, means extending the conjugation of the double bond, the best thing you may get is an aromatic compound. So like alkenes, aromatic ring might also be considered to include sp2ch and cc double bond. Does this mean IR spectra are similar to alkenes? Let's see. In the IR spectrum of toluene, what are the significant peaks, that is 4000 to 1450 per centimeter, reveal the presence of benzene ring? So you can look at this and compare the previous one. A benzene ring consists of 6 sp2 carbon connected with alternating single and double bond, and it has significant resonance delocalization of its pi electrons aromaticity. The resonance hybrid suggests all 6 CC bonds benzenes are more than a single bond, but not complete double bonds. A partial double bond is not as strong as a full double bond. So the stretching frequency of the aromatic CC bond is predicted to be lower than the alkene double bond. So because of the resonance, because of the aromaticity, because of the difficulty in discriminating the single bond and double bond in case of aromatic compound, a benzene, so the stretching frequency appear a bit lower than the double bond. IR spectrum of many benzene ring compounds reveals that the benzene ring CC stretching pattern occurs a pair of peaks, one at 1625 to 1575 per centimeter and the other one at 1525 to 1475 per centimeter. Up to 4 C double bond C stretch peaks can occur in this region depending on the nature and the number of the benzene rings substituted. Look at the infrared spectra and ensure that what I have said is correct. So we have kept a question pending. What is that? Is what are the factors which influence the shape of the spectrum? Let's come back to the point later. Thank you.